in section 3 of chapter 1, we're going to start looking at how we describe and summarize quantitative variables. And a lot about what we talk about in section 3 is going to carry on for future chapters in statistics, especially chapter 2. So when we're describing distributions in statistics, we just are looking at 4 things, and we can use the acronym SOX. So S stands for shape, O stands for outliers, C stands for center, and S stands for spread. Now, it is important here that the first S is shape and the last S is spread. We do look at these things in the order in which they are listed here, so it does matter where they are placed. So once we've graphed a quantitative variable, describing what we see helps identify patterns and answer questions we might have about the data. Now, an important thing to note here is that we don't use this acronym for categorical variables, and there's 2 main reasons. The first one being that categorical variables are not numerical. There's a lot of numerical things we're gonna start looking at when it comes to outliers, center, and spread. And those can really only be done if you have numerical values. The second thing is that in categorical variables, the x-axis does not need to be in order. So because with categorical variables, the x-axis is a word, you can choose to put those variables in any order you want. You could do alphabetically, least to favorite, the order in which they show up in the data set. It really just depends on what you're doing. So that one more goes along with shape. So shape, if everyone has the same set of data, everyone should be getting the same shape for their distribution. So we need to make sure we're dealing with quantitative variables where the x-axis is going to be in order from lowest to highest number. So that brings us right into what I was just talking about, shape. So once we graph a distribution, the first thing we do is identify the shape of the graph. So when we're looking at the shape of our graph, there are 3 main types of shape: unimodal, bimodal, and uniform. So when we talk about unimodal graphs, what that means is they have one hump. Now, we can have one hump where it's symmetric, which is what we're going to talk about in a little bit, or we can have one hump where it's skewed in a specific direction, which we'll talk about in a little bit as well. So it just means that there's one curve or one hump, if you will. Whereas bimodal means you have 2. Now, bimodal can be symmetric, where they're the same, or they could be where one of the humps is bigger than the other. All we know is bimodal has 2 humps. And then we have uniform, which is easier to describe with bars, and that's when all of the bars are roughly the same height. So the distribution is the same going across. There might be like one that might be slightly taller, but for the most part, they're approximately the same. Now, the 3 that we're going to care about most are symmetric, left skewed, and right skewed. So symmetric is when there is an even distribution. So the most common one that we're going to see is symmetric with the 1 hump. We can be symmetric with 2 humps as well. We're not going to look at a lot of data that is bimodal by nature, so you're not going to see a lot of symmetric with bimodal for this course. The one that we're going to see the most is symmetric with reference to unimodal. So as I kind of mentioned earlier with the unimodal, your data could be skewed in one direction, and that's either left or right. Now, when we talk about skewed, we are looking at the tail of the data and where the tail of the data appears. So for left skewed, the tail is at the left end. It's at the lower end of values. So tail is at lower end. A lot of people get confused with left skewed and they think that it's where the hump is, and that's where it is, but it's actually where the tail of the data is. So with a left skewed graph, your tail is at the lower end. Whereas with a right skewed graph, your tail is at the higher end of your data. Now, when we talk about lower end and higher end, we're talking about in relation to your data set. So the lower end doesn't need to necessarily mean small numbers. It's small in relation to the data set. And higher end is higher numbers in relation to the data set. Okay. So if we're being asked to describe the shape, we might use one word like symmetric. We might use two words like bimodal and symmetric. So we're going to look at a couple examples here. So we want to draw a symmetric bimodal distribution, which I did above when I was doing symmetric. So just means two humps roughly the same height. We can also draw a unimodal right skewed distribution, which looks like what we have above for right skewed. The next thing that we're going to talk about briefly here is outliers. Now we'll get more into outliers later on in this section, but an outlier is an individual piece of data that falls outside the overall pattern of distribution. And it does say individual here, but depending on how large of a data set you are looking at, you might have more than one outlier. But by definition, it's a single piece of data. Now, when we're finding outliers, it is important that we know why it occurred. So sometimes it occurs because of a mistake. So that's why you always want to double check your data when you're graphing it or writing it down if you're collecting data. So you could have written it down incorrectly, input it into your calculator incorrectly, so you always want to double check. So that's why we always plot the data first, because our eyes can usually tell us if an outlier exists. And on certain occasions, we can eliminate outliers from the data if there's a good reason. So right now, we're not going to talk about how to mathematically determine, because sometimes it's not obvious. You might be on the fence of, well, this is a lot different than the rest of the data, but is it different enough? So when we're calculating outliers, the very first thing you want to do is plot it. Then you want to determine whether there is an outlier, and if it is, make sure that the data is actually accurate. And lastly, determine if there's a valid reason that the outlier can be removed. So depending on what the data describes, you might be able to remove the outlier, you might not. If there isn't a good reason, don't remove it, just identify it as an outlier. The next thing we're going to talk about is center. And there's 3 different ways you can technically measure the center in statistics. And that is through mean, median, and mode. And we're going to talk about each of these individually and then discuss them all at the end. So in this table, I have gathered data on how many siblings, Steph and Half included, of a class, and we've copied it down below. And I did have 25 students, so there is a single piece of data outside that you're going to want to make sure you include. So it's important to know here that we've typically referred to mean as mean or average in the past, but average is a generic term for the measure of a center. We need to be specific. So when we say average, are we talking about mean? Are we talking about median? Talking about mode? So usually you're referring to the mean, but in statistics, we don't use the word average. We use the words mean, median, or mode. So we need to be specific in what we're talking about. So the formula for mean, so in the past, you may have just been told add up all of the numbers and divide by the total. But in statistics, we come up with formulas for things. So in the formula for calculating the mean is x bar equals sigma x sub I all over n. And I am going to go over what each of these represent. So x bar is the symbol that we're going to use for mean of a sample. And it is important here that we are distinguishing that it's a sample. We'll talk about populations later on. X sub I is each individual observation. So I could number my data for a number of siblings as x sub 1, x sub 2, x sub 3, all the way up until I reached my total number of observations, which is n. And then we have our capital sigma, and what it means is add up. So if I were to take these variables and transfer them to words, it's telling me that the mean equals the sum of each observation divided by my number of observations, which is what we've been told in the past. So yes, there's a formula. Do you have to write it out? No. So if I were to use my class data, add them all up together and divide by 25, I would get a mean of 1.08 siblings. Now, when we're talking about center and in a little bit spread, it is important that we include units for our data. So typically we'll just indicate it as x bar equals. So we don't usually write mean number of siblings is 1.08 siblings. Typically we just write x bar equals and then we put 1.08, and that's where we need to have the units to indicate that we're talking about siblings so we know what the data is describing. So the reason we don't always use mean is because mean always has to include outliers. So we just talked about how outliers can affect data. So for instance, we have a list of 7 scores for 7 exams: 90, 92, 94, 98, 86, 88, and 0. Now obviously there is a very clear outlier here, the 0. There might be a legitimate reason to eliminate the outlier, one of those being that maybe the student was absent the day of the test. So currently they do have a 0, but the next day they come to school, they take the test. Hopefully, it's in line to similar scores they've received. Now, if we cannot eliminate the outlier and we were to calculate our mean, we would get 78.29, which is a lot lower than any number in our data set if we include the 0, because the next lowest score is 86, so you would think the mean should be higher than that. Now, if we were able to eliminate that outlier, our new mean would be 91.33, which is much more in line with what the data tells us that it should be. So the outlier here is bringing down the mean. Now, a mean can also have the opposite effect as well. If you have an outlier that is a lot bigger than the rest of your data set. So suppose on the reverse side of things, we had a lot of scores between 15 and 20, and then we had a 76. That would bring the mean up higher than it probably should be. So the mean is something that we call non-resistant. And what this means is that it is strongly influenced by extreme values or outliers. So if you do have extreme values in a data set, the mean is not as reliable as a measure of center. And that's where median comes into play. So median is resistant. It means that if there are extreme values in a data set, the center will not be as affected by it. Because when you're calculating median, you have to put the data in numerical order, and you find the middle value by crossing off values at the ends. So the first values that are going to be eliminated in calculating median are those extreme values or the outliers. So for example, I have already ordered the data from our table on siblings from lowest to highest. So there are 4 zeros, 16 ones, 4 2s, and a 3. So if I started crossing my data out at the ends, I would start with my 0 and my 3, and I would start working my way in. Now, I'm not going to keep going at this point, because once I've eliminated all the numbers that aren't 1, that indicates to me that my median is 1. I could keep going and eliminating all the 1s, but I'm going to be left with a 1 at the end. My mean, if you remember, was 1.08. So if I'm looking at this, my mean and our median are very close together, which is a good thing. So that tells me that the closer your mean and your median are together, the more symmetric your data is. Now let's take a look at the exam score example. So again, in calculating the median, I'm going to start by crossing off at the ends, and you can see the first thing to go is that 0, and it leaves me with a median of 90. Now, I do have to use the mean I calculated with the 0, which is 78.29, and I can see here that these are further apart. All right. They are not close together. So we can see here where median was the better choice. Now, when they're very close, you could use mean or median, but in that case, we would go with mean because it is just a tad bit more accurate for the middle versus the median. All right, so we're not saying that the median is always a better measure for the center, but whenever you have extreme values or outliers, the median is the better measure for the center. So we don't have a special formula or a special math symbol for median. Usually I just abbreviate it MED. So the last measure of center is one we're never going to use because it's useless, and that's mode. So mode finds the most occurring value in the data set, and that most occurring value can happen anywhere in the distribution. It could be the smallest number, it could be the biggest number, it could be in the middle, it might not. It doesn't have to follow the shape of the distribution. So if you have a symmetric shape, it doesn't necessarily mean that the mode is in the middle. It could be left skewed, it could be right skewed, the mode could be anywhere. So we don't use mode at all for center, ever. So the next thing we're going to do is take a look at some examples. So we have 3 lists of data here. We're going to make a histogram of each of our data. We're going to calculate the mean, median, and mode, and then we're going to take a look at the shape of the distribution. So the first set of data we have is 78, 79, 80, 80, 85, 91, and 100. So when I am doing my histograms, I'm going to go up by tens. So we're going to do 70, 80, 90, 100. And I do have to do 110 because remember, when we're doing these histograms by the classes, I'm assuming my first class is technically numbers between 70 and 79, and 80 isn't included until the next one. So between 70 and 79, there are 2 pieces of data. Between 80 and 89, there are 3 pieces of data. Between 90 and 91, there is 1 piece of data. And between 100 and 110, there is 1 piece of data. So if I add up all of my numbers and I divide, I'm going to get a mean of 84.74. 0.71. Okay. My median is going to be 80, and it just so happens that my mode is also 80. So in this case, mean, median, and mode fairly close together. If I'm trying to come up with a shape for this graph, I would say that it's mostly symmetric. I have had people say, well, it kind of looks like it might be right skewed. but we're going to take a look at a couple more examples where it's more obvious, right skewed and left skewed. So our next set of data is 77, 77, 78, 79, 85, and 100. So I'm going to set up my histogram with the same scale. So between 70 and 79, we have 4 pieces of data. Between 80 and 89, we have 1. Between 90 and 99, we have 0. And between 100 and 110, we have 1. So remember, if you don't have a value that falls within a class, you don't put anything there. Okay? So when I'm calculating my mean, I'm going to add up all of my numbers. And then this time I'm going to divide by 6 because there's only 6 numbers there. And we're going to get 82.67. For my median, I end up, because there's an even number, I've narrowed it down to 2 numbers. Now, typically the way I would say to calculate the median when that happens is add them together and divide by 2. But since 78 and 79 are right next to each other, I know that 78.5 is in the middle. And then my mode in this case ends up being 77. So in this case, we can see how mean, median, and mode, they're all fairly different numbers. There's not a lot of similarity there. And if I look at my distribution, most of my values appear at the lower end. And when that happens, we're looking at a right skewed graph. Now, one thing you may want to add to your notes here in addition is that when we have a graph that is right skewed, the median will always be smaller than the mean. So I would add that somewhere in your notes. Right skewed, the mean is bigger than the median. Last set of data. So first I'm going to set up my scales. So between 70 and 79, I have 2 pieces of data. Between 80 and 89, I have 2 pieces of data. Between 90 and 99, I then have 3 pieces of data. And I don't have anything bigger than that. Okay. So I'm going to add up my numbers to calculate my mean. I'm going to divide by 7. And I'm going to get 86.29. When I calculate the median, I end up with 89, and my mode ends up being 73. So in this case, the majority of my values end up being at the higher end. So that means we're looking at left skewed. So when we have left skewed data, the mean is going to be less than the median. Okay. So when we are looking at the graphs of these, just one more time. Unimodal symmetric. So in this case, remember the mean and the median are going to be about the same. They're not required to be identical, but they're going to be relatively close. Left skewed is when the mean is bigger than the median. And in right skewed, we get that the median is bigger than the mean. Now, I didn't reference mode here because mode we're not really going to be looking at. I can include mode here. Like we can see that with symmetric, mean, median, mode, all roughly the same. With left skewed, we can see that the mode is the smallest value. And with right skewed, we can see that the mode is in the middle. Like we could add that if we wanted to. It's not necessary, and I'm not going to because mode is not a useful thing to describe center. we're going to be looking at mean and median only. The next one we're going to look at is spread. Now, one of these you might have seen before, the other two might be new. So in statistics, we look at range, standard deviation, and something called IQR, which stands for interquartile range, which that's the one that most people have not heard of. Some people have heard of standard deviation before, some haven't. Everyone's typically heard of range before. So where range differs from what you've heard before, range is sometimes an interval. It's like, oh, my range of values from 0 to 100. Well, in statistics, the range is a difference. So the range is a single number. And the way we find the range is we take the max from our data set, we subtract the min, and that value equals our range. So again, range is a number, not an interval like you may have seen in the past. Now, standard deviation is an average deviation of an observation from the mean of the data set. So in other words, standard deviation tells us how far on average each value is from the mean. So before I just introduce the formula and then walk you through an example, I'm going to walk you through an example first where we calculate standard deviation by hand so you understand the process. Then I'm going to introduce the formula. Now, we will learn how to do standard deviation by hand because it is necessary to understand where the formula comes from. But we will also be discussing how you can find standard deviation in the calculator, how you can check your work, especially when you're required to do it by hand, to make sure that you didn't make any mathematical errors. So in our example, a group of elementary school children were asked how many pets they have, and we have their responses arranged from highest to lowest. Now, when calculating standard deviation, it is not required that you put the data in order from lowest to highest. They can be in any order. The very first thing you do when calculating standard deviation is find the mean. So the mean for my data is 5. Now, very rarely will you get data where the mean is a whole number. Majority of the time, you're going to get a standard deviation mean that's a decimal. But for our purposes, it's nice to work with a value that's a whole number. So from each of our observations or pieces of data, we're going to subtract the mean. So I'm going to do 1 minus 5, which is negative 4, 3 minus 5, which is negative 2, 4 minus 5 is negative 1, and there are 3 of them. 5 minus 5 is 0, 7 minus 5 is 2, 8 minus 5 is 3, and 9 minus 5 is 4. It is important here that we always take the data minus the mean. And the reason is when we have decimal means, the order of subtraction is going to matter. When you have whole number means, it's not as important, because no matter what order I did it, if I did 5 minus 1 or 1 minus 5, I'm still going to get 4. And since my next step is to square that deviation, it doesn't matter which order I did it in. But if my mean had been 4.7, 1 minus 4.7 and 4.7 minus 1 are two different numbers. They're not the same positive and negatively. So it is important that we do the observation minus the mean. So because standard deviation is a distance, and distance can't be negative, once we do that initial subtraction, we're going to square those numbers so we end up with positives. And when you square a negative, you get a positive number. So if you're doing this by hand and you square your deviations and you get a negative number, you need to fix that because you should not get a negative number. So you should get 16, 4, 1, 1, 1, 0, 4, 9, and 16. The next step is to now compute the average squared deviation. So what we're going to do is find the sum of the squared deviations, which I'm going to abbreviate. So I'm going to add all of those numbers together, and we're going to get 52. Now, typically, with mean, we divide by n. But with standard deviation, we're actually going to divide by n minus 1. I'm not going to go into the reason behind it, but I can tell you that for samples, we will always divide by n minus 1 with standard deviation. There is something called population standard deviation if you were looking at all of the data, and that involves dividing by n. But when you're looking at a sample of data, you have to divide by n minus 1. So in this case, that means dividing by 8, because there are 9 numbers, 9 minus 1 is 8, and that gives us 6.5. So the value we get, 6.5, is called the variance, and it's the average squared deviation, or distance, of the number of pets the group of elementary children have. So with this, we have an average squared deviation, so because of that, the units are squared pets, because we squared numbers. And variance and squared pets, pretty useless because no one talks in terms of squared distance. So what we have to do to get rid of that squared, so we have pets and not squared pets, is we take the square root. So we have our variance, 6.5. We're going to take its square root, and that's going to give us our standard deviation, 2.55, which is going to have the units of just pets. So we can say, on average, each value is about 2.55 away from the mean. So now that we have looked at an example, I am going to write down the variance formula. So the symbol for variance, and I'm actually going to go with the symbols first here before I write the formula. So the symbol for variance is S sub x squared. Mean is still x bar. Each individual observation is x sub I. We still have n for the number of observations and sigma for the sum. So that means my formula for variance, S sub x squared equals the sum of each observation minus the mean squared all over n minus 1. Okay. The standard deviation formula is just one step further, and that's to take the square root. So standard deviation is the symbol S sub x, because we're taking the square root of both sides for variance, equals, and then it's just the square root of the variance formula. So square root sigma x sub I minus x bar squared all over n minus 1. And I know standard deviation is a scary formula. There's a lot of symbols, there's square roots involved, but as long as you know the steps, the formula is not necessary to have memorized. As long as you know the steps, find the mean, subtract it from every value, square those numbers, add them together, divide by the square root of n, then take the square root. So if you can verbalize the steps, that's what's important. So if we're interpreting our standard deviation in context, the number of pets typically varies from the mean by 2.55 pets, because that's what we got when we took the square root. So it measures the typical distance of the values in a distribution from the mean. So when we're talking about using standard deviation as the descriptor for the spread, because standard deviation is calculated using the mean of a data set, you should only use it when mean is your chosen measure of center. If you're using median, you're going to want to use range. So range and median go together, standard deviation and mean go together. Okay? So a couple of things. When we're looking at standard deviation, it is always greater than or equal to 0. Okay? So standard deviation can be 0, and it is specifically 0 when when all values in the data set are the same. So standard deviation is talking about average distance from the mean. So if the distance is 0, it means the values are all equal to the mean, which means they're all the same. So standard deviation has the same units of measure as the original variable. So standard deviation and mean have the same units. And then because it involves using mean, it is also non-resistant. So that means just like mean can be affected by outliers, so can standard deviation. So that a few outliers can make it larger or smaller depending on where those outliers fall. So if your outliers are a lot lower than the rest of your data, it will pull the standard deviation lower. If your outlier is a lot bigger than the rest of your data set, it will pull the standard deviation higher. So the greater the standard deviation, the greater the variation of the distribution. So whether or not a standard deviation is small or large is relative to what your distribution looks like. So we'll talk more about that when we're looking at examples. Okay. The last measure we're going to look at is IQR. So IQR stands for interquartile range, and it uses percentiles to describe the spread of the distribution. So if you recall, percentiles measure the percent of the observations that fall below a value. So if the median is the middle of a data set, so 50% is below and 50% above, when we're talking about what percentile it's in the 50th percentile, because 50% of the data is below. We don't usually talk about above, we usually use it below. So other percentiles, the 0th percentile, which we typically don't use that term, we refer to it as the min. It's the lowest value in your data set. The 25th percentile is known as the first quartile. Which we just abbreviate using Q sub 1. So 25% of the data is below this value. The 50th percentile, that's the median. It's where the middle is. The 75th percentile is known as the third quartile, which we abbreviate Q3. It tells us 75% of the data is below this value. And then we have the 100th percentile, which we refer to as the max. It's the highest value in the data set. Now, normally in statistics, we don't actually use the term 0th percentile or 100th percentile. Usually the highest percentile you'll see is 99.9%. We don't like to deal with absolutes like saying, yeah, I'm in the 100th percentile. So that's why we don't use 0th percentile or 100th percentile. We use the words min and max. This will be the only time you hear me say those words. So these numbers make up something that's called the 5-number summary. So there are 5 numbers. They summarize all of the quartiles or percentiles in some data. So it's a bit time consuming to calculate these by hand, and I'll show you how you can calculate them on your calculator here in a little bit. So in order to calculate all of these values, because it deals with finding median, you have to place them in order and then start by finding the median. Then you find the middle value to the left and right of your median to identify the first and third quartiles. The min and max are pretty straightforward. So here is some data from a previous class on how many hours of sleep they get before the first day of school. And we're from anywhere from 2 to 8.5. So the first thing we want to do is find the median. And instead of crossing them off, because I'm going to need them again, I'm going to place dots so I know when I've used them. So because I'm left with 2 7s in the middle, I have to split it up, and my median is still going to be 7. But one of the 7s is in the lower 50%. The other 7 is in the upper. Okay, so this is where I get my median, 7. So now, the lower values before that, I'm going to use that to find my first quartile. So I'm going to place the dots again, but this time in red. Okay, and I get a specific value here. I get 6, and that's going to be quartile 1. Okay. I'm going to do the same thing with the numbers above 7. I'm going to find the median of those. This time I'm using blue. And I get the number 8. Now the min and the max are pretty straightforward. So my smallest number here is 2. My biggest number is 8.5. So I don't have to do anything special mathematically to calculate the min and the max. So the IQR, the interquartile range, so if you think about it, inter is middle and then quartile. So I want to find the range of the interquartiles. And what that means is the interquartiles are the ones between the min, the median, and the max. So that's quartile 3 and quartile 1. So I take quartile 3 and I subtract quartile 1. So just like range, regular range, interquartile range is a single value. It's not defined as an interval either. So our interquartile range here, my quartile 3 is 8 minus my quartile 1, which is 6, tells me that 2 hours is the IQR. So the interquartile range is 2 hours. Another thing, so the last graph we're going to talk about here in a second is a graph we can make based off the 5-number summary. And that graph is called a box plot. So using our 5-number summary that we just calculated, we are going to draw a box plot. So box plots are pretty straightforward. So they only have an x-axis. And your x-axis is your label based on what we're looking at. So we're looking at hours of sleep. Okay. When you are labeling your axis, you start with the lowest value and then you want to go to the max. Now I am rounding up because the max is a decimal. So 2, 3, 4, 5, 6, 7, 8, and 9. So the first thing we're going to label is our min, and we're going to place a dot. And then we're going to label our max, and it also gets a dot. Okay. The box comes from quartile 1, the median, and quartile 3. So quartile 1 started at 6, quartile 3 was at 8, and that's how we're going to create our box. And then we're going to label the median 7, and we're going to connect them with lines. So we've got our min, quartile 1, median, quartile 3, and our max. So I mentioned before that we would eventually talk about how we can calculate outliers mathematically, and that comes from the 5-number summary and the IQR, and it's called the outlier test. So you have to have the 5-number summary in order to calculate outliers. You then need the IQR, and then you do 2 things. First, you do quartile 1 minus 1.5 times the IQR, and any data below that number is an outlier. You then do quartile 3 plus 1.5 times the IQR, and any data above that number is an outlier. So it doesn't really have a fancy mathematical formula either. So we're going to go ahead and calculate it for the hours of sleep. So IQR was 2, quartile 1 was 6, and quartile 3 was 8. So for the lower one, we do quartile 1 minus 1.5 times the IQR, which is 2. So that becomes 6 minus 3, which is 3. So I look for any number less than 3. And there is a number less than 3, and that number is 2. Now we're going to do with our upper. So quartile 3, 8, plus 1.5 times the IQR, which is 2, which gives us 8 plus 3, which is 11. So now I'm looking for any number bigger than 11. And our biggest number was 8.5. So there's no outlier that comes from that. So 2 is the only outlier. Okay. So with box plots, so the nice thing about constructing box plots is if you know you have an outlier, you can then modify the box plot to get rid of that outlier. So the box plot identifies the outliers for us. So it's a nice way, like if you initially graph your data in some different way and then you're calculating outliers and you find them and then you want to regraph it as a box plot so that you can identify those outliers, that's the best way to do it. So for our modified box plot, I'm still gonna label my x-axis like I did before, and we're gonna have hours of sleep. I'm still labeling it with all of my values. But since 2, which was my min before, is an outlier, I'm going to denote it with an asterisk. And that's going to denote an outlier for my min. And then I'm going to start with the next smallest value, which is not an outlier, as my new min, which is 4.5. My median, my quartile 3 and my quartile 1 are not changing, and neither is my max. So now I have a new box plot, which looks different. It actually looks a little bit more symmetric than the other one because my min and my max are closer to the rest of my data. So we can see how modified box plots can give us a nicer looking graph. And those lines are technically called whiskers. So if you've heard of a whisker and box plot before, those are called whiskers, the lines we draw to the min and the max. So the next observation is more acceptable for us for those whiskers when we get rid of outliers. So the last page of notes here is how to create a box plot on your calculator. So I'm going to go through these steps, and I would like you to follow along on your calculator. And if you are still struggling with it, please reach out to me in class, and I can go through it with you individually. So when we did the histogram on our calculator, we had to start by entering our data into a list. And we're going to start off the same way with box plots. So you enter your data into list 1, you go to plot 1 like you did before, but this time when you're choosing the graph, you chose the histogram, but this time you're going to choose the box plot, which is the 5th one. Depending on how your screen displays it, it's the bottom middle, okay? You can also, so that's a regular box plot. So this is a regular. You can also do a modified, and that's what the other one here is. This is a modified box plot. So it does both. And then you just, once you select the graph, whether it's modified or regular, you hit zoom and then 9, and it'll fit it to the screen. So I want you to go ahead using the data we did before. Try it with each. Make sure you know how to do it, and then if you have questions, let me know. The next thing we're going to talk about are all of the statistics we calculated today. Your calculator will do for you. Mean, median, standard deviation, the 5-number summary. Your calculator does it for you. You could ignore the part about the AP exam. Typically how it's going to work for me is I'm going to give you the list of data. You can put it into your calculator to find the summary statistics. So you start off the same way you would with a graph. You go into list 1 and you enter all of your data. You're then going to go to stat and then go over to calc. And you're going to choose the first option, 1var stats, which stands for 1 variable stats. For right now, it should automatically draw from list 1. And then it has something called frequency list. Leave that blank for now. We'll talk about in chapter 2, we'll talk about our frequency list. So once you do that, it then gives you a summary. So X bar is the sample mean, just like when we were calculating them. The sigma X is the sum of all of the values in the list. So if you're working through the standard deviation by hand and you want to make sure, mean by hand, you want to make sure you added them all together. Then you have the sum of the values in each of the list after each of them was squared, which is not something we're going to be looking at. S sub X is the sample standard deviation. So this is the sample standard deviation. This is the one that we're going to be dealing with right now. The next one is sigma X. Which is population standard deviation. We're not going to be using it now. Ignore it. We're going to be dealing with sample. And then N is the total number of items in your list, which should match the N that you were given. So if your N doesn't match, you know you've missed a value, so you want to go back and check. The next 5 things, the last 5 numbers, after you scroll down, is the 5-number summary, and it goes in order. Does the min, quartile 1, the median, quartile 3, and the max. So using the list that you have for your box plot, go into 1 variable stats, make sure it matches everything that we calculated, make sure that you know how to do it. Again, if you're struggling with it, if you have questions, please let me know. Not only about the graph stuff and the calculator stuff, but anything from this section.